Hi, Faye.
Morning.
How you doing this morning?
Tired.
I can understand that. Yeah. Oh, you want to know something ridiculous?
Yes.
All right, I have one of my lovely little Super A students in my Chem 1 lab or my intro lab. Do you remember back in intro where Dr. Musgrave used to make you put the unused answer as a number? Do you remember that?
Yep.
All right. Out of 280 points, she failed to put the unused answer in 8 of them. So she lost 8 out of 280 points. And she
Wow.
wanted me to fix it.
Well, that's happening in my Chem 1 class lecture, but I'm taking it strictly online. But there's a lot of unused answer numbers.
Dr. Musgrave?
No, it's with Kathy Mitchell, but I guess the tests are from him.
Oh yeah, her tests are very interesting.
Yeah.
I mean, that's especially ridiculous for a test. I mean,
Oh, yeah.
it's ridiculous to begin with.
Well, it's definitely on all the quizzes and some of the tests. I don't remember the no use, not used on many of the exams, but it is on all the chapter quizzes or module quizzes.
Honest to God, what is the whole logic behind that? The fact that you physically had to put the not used answer in there so that you can't claim that, oh, I mistakenly put this answer when I meant this. I mean,
no, it's not only that too. I literally had a question and it had 10 possible correct answers. So I had to literally select, I think, 30 not answers because you have 3 or 4 ABCs for each answer. And it's just a ridiculous amount.
Yeah,
guys, that is what the SSI is for. I mean, you have the power. You do have the power to make these things known. All right. Sorry.
Well, she mainly uses it for dimensional analysis, and I think it's just so you can't, I don't know.
I really don't know the purpose of it. Other than what I said, that the student can't come back and claim that they mistakenly put this answer in there. I mean, I don't know the logic behind it. Whatever. I'm sorry, guys. I have 2 more years to deal with this, and I'll be done with it forever and ever. Then I'll be on a beach in Provence somewhere. You can come and find me. You can come and find me and get me an umbrella drink on that beach in Nice. Okay. How are we doing other than that, ladies and gentlemen?
Good.
Have we got our bitches out right now?
Yep.
All right. Anything about me? Do you need to bitch about me?
No, the last lab was fantastic. I was actually able to get through it, even though I'm really dumb.
Get through the absorption lab, Samir?
Yeah.
Good.
Oh, I have one question about the calculations because I didn't. Hold on. For the last, to get the.
Are we talking about?
Well, I got the molarity of the diluted solution, and I used the M1 V1 equals M2 V2, and then I plugged the that into M1 V1 equals M2 V2 for the unknown original, but I obviously put the diluted concentration that I got on the V2.
Well, what I'm perceiving you did, Faye, was you put the diluted sample next to the concentrated amount you added. All right, what you were supposed to do, you added 30 milliliters of your Gatorade straight into the 250 volumetric, right, Faye?
Yeah.
What I'm perceiving that you did was you set up your M1 V1 equal M2 V2 as your diluted sample, your diluted concentration times the 30 is equal to X over 250. Is that what you did?
No, I did M1 times 30 milliliters equals the diluted unknown times 250. Oh, no, but I didn't do the algebra right. Never mind. I divided the wrong thing.
Okay. So
Never mind.
basically all you had to do is take the molarity, multiply it by that 0.250 liters, and then divide it by 0.030 liters, or 250 and 30.
Okay. And it's the same. I know concentration is liters per or moles per liter, but when I did the calculations with milliliters, it's literally the same answer, right?
Yeah, absolutely. Because what you would have to do is on the left side, you'd have to multiply it by 1 liter over 1,000 milliliters, and on the right side. So those cancel out, those conversions cancel out. So you can use just
Okay.
liters and milliliters.
Okie dokie. Okay, thank you.
No problem. Charlie,
Yes.
did you give up on me? Weren't
I
you
don't think so.
weren't you supposed to be coming into another class or something?
Yes, but I don't have to go into my internship for this week.
Okay. Remind me
or-
again. Send me an email. Okay.
Okay,
Reminding me to send the invitation to you. All right.
that's fine. I just didn't want to say anything because I didn't need the invitation, so I was just gonna hop on here.
No problem. No problem.
Thank you.
Guys, today's lecture is fairly easy. One calculation, one simple calculation. And the other nice thing about this is the same explanation I used to use on the stand, because when I was testifying, I have to explain what I'm doing. And I literally would use this analogy when I was on the stand testifying as to how I analyzed drug samples. So it's a little bit of a sideline. And you guys have all done this. Tell me who hasn't spilled coffee or spilled Kool-Aid or something. And then you put the paper towel in, and you notice how the paper towel sucks that liquid up. Am I right?
Yeah.
All right, if you take that same paper towel and the brown liquid from the coffee gets carried up. Now, when you dry the towel, isn't that area where the liquid went to, isn't that kind of like a small little ring of brown there? Do you know what I'm talking about?
Stain?
Faye?
Like a stain?
Yeah, like a stain.
Yes.
So you guys have done this before. You have done the same exact experiment. You just didn't know that you were doing it. And this was basically studied by a botanist, a Russian botanist around 1910. And this guy, Mikhail Twisset, he used diatomaceous earth. Diatomaceous earth is ultra purified earth that ends up being white. And what he did was he put this into an open cylinder. Then he took some plant material and he extracted the plants with something like wood alcohol or something like that. So that instead of jamming solid plants in there, he extracted some of the stuff out of the plants and that dissolved in the wood alcohol. Then he put this extracted material and he put it down near the bottom of this column of diatomaceous earth. And he immersed the cylinder in a solvent. And what he noticed was he got different bands that appeared. And each one of these bands was a new chemical. Since chemicals have different chemical bonds, they adhere to the diatomaceous earth differently, and they go up this column at different rates. Now, has anybody ever seen a DNA? They like to call them barcodes. Has anybody ever seen one of those pictures of that? No?
Pictures of a barcode or like a DNA barcode?
Well, it kind of like looks like this same thing, only instead of being colored, it's black and white.
Yes.
DNA analysis uses this same principle to separate out the different strands of DNA. And that's how they're basically able to say, okay, I got a band pattern of DNA from the crime scene. It matches this guy's DNA band pattern, must be him. And they do a statistical analysis, which makes it improbable it's contributed by anybody other than somebody that's a twin. What's the kind of twin that there are two types of twins? One is made from two eggs.
Fraternal and identical.
Identical twins. Identical twins have the same DNA. And what's the other kind, Faye?
Fraternal or paternal?
Yeah, fraternal. Thank you. I'm sorry, I'm losing my mind here. Fraternal twins do not have the same DNA because they come from different eggs. Identical come from the same egg that splits. So they have the same DNA. Another, it's a sideline that you don't really need to know. But in any case, what I'm trying to say is they use this stuff daily. So it is a technique that's used. Now, what he did when he did this, if you see that, there are different colors of the different materials. So basically, because of that, that's where you get the chrome in chromatography. There's not really a color analysis here, but that's how it developed because of the colors that were in the original pattern. So what actually is it? And it's nothing more than a separation or a purification technique that involves the use of a stationary media that has access to a mobile media. And what's happening is the job of the mobile media is to force these chemicals through the stationary phase. The job of the stationary phase is to prevent the mixture from moving. And it does this because the individual compounds each have their own chemical bonds. And they're bonded to the stationary phase, but the mobile phase comes along and pulls it off for a little bit. Then it gets bonded back to the stationary phase. Mobile comes along, moved along. And it's because different chemicals have different chemical bonds. They adhere to the stationary phase and the mobile phase at different rates. So as we're pushing this through the entire stationary media, because the different chemicals have different chemical bonds, they adhere at different rates. They go through the media at different rates. All right, let me give you the analogy I used to use on the stand. Picture you have this big long hallway, and the hallway is lined with Velcro. And you throw a tennis ball and a racquetball down this hallway. The tennis ball, because it's fuzzy, will adhere to the Velcro, and it will go down this hallway at a slower rate than the racquetball, which is smooth. And that's basically all we're talking about in chromatography. Now, we have different chromatographies, and they're defined by their stationary phase and their mobile phase. What you're doing is today is you're doing thin layer or paper chromatography. The solid is your stationary phase. The paper is your stationary phase. The mobile phase is some sort of solvent that moves through the stationary phase. Gas liquid chromatography, used all the time. It has a stationary phase of a liquid that kind of lines the inside of a big long tube. So you put these molecules, which are made gaseous, and you put them through this tube and they dissolve in this liquid for a little bit. But this tube's placed under a high temperature, like 300 or 400 degrees Celsius, and it's placed under a high gas pressure. The combination of those two things force these molecules through this long tube. You have another one that you may end up hearing, and it's called high pressure liquid chromatography. And what you have there is you have this big long cylinder that's about maybe that much in diameter. And this is filled with diatomaceous earth, purified earth. And what you do is at the very bottom of this column, you put your sample. And the earth will prevent the compounds from moving up. But again, it's in a liquid, it's a mobile phase, and it's put under high pressure. That combination forces these things to separate. So we're using a paper today. So what you're going to do, what you do in this experiment, if you were performing it, first thing you would measure out a space 1.5 centimeters from the bottom of the piece of paper, and you mark it with a pencil. Anybody want to guess why you don't use pen?
It'll soak it up and mess up the results.
The pen also will go up the paper. And because the pen goes up the paper, you're going to distort your results. So you're going to mark that pencil line at 1.5 centimeters from the bottom. Then you are going to put all your known samples about 1 centimeter apart on this pencil line. You're putting them 1 centimeter apart so they don't contaminate one another. Then when you have all your known materials and your unknown on this piece of paper, you fold it into a cylinder and you put it into a chamber. Then begins the real exciting part. For 45 minutes, you get to watch this thing creep up to the top of the page. Then finally, after 45 minutes or so, it gets up close to the top. You take the paper out, you take the tape off so that you have a nice flat piece of paper, and you take a pencil and you mark how far the solvent went. Then you calculate what's known as the retardation factor. This is the only calculation you have to do. Retardation factor, or RF, is the distance that your spot moved, the distance your sample moved. And you measure that from the direct center of your spot. That gets divided by the distance the solvent moved. So if I'm looking at a TLC plate and I'm looking at my green spot over here, if I am going to calculate my RF, all I'm going to do is take and measure from where I started to how far this spot moved up the plate. That's going to be my distance that my sample moved. I'm going to divide that by the origin to where the solvent moved. Say the distance my solvent traveled was 1.75 and the distance to the center of my spot was 1.19 inches. All I got to do is divide the 1.19 by 1.75. Inches cancel, so RF has no units. That is what the answer is. Now, nudge, nudge, wink, wink, hint, hint. You will see this again. Understand this, because this is going to be worth points in the final. I'm telling you flat out, you need to know this, all right? Don't lose these points. They're too easy, okay? Now, basically what happened was it was originally thought, well, all I have to do is measure all these RFs and I can create this huge table that all I have to do is note what my solvent is and note the RF, and I can look and find and identify my unknown. The trouble is there are too many variables. Temperature. If you increase the temperature. Don't you increase the solubility? If
Yes.
you increase the solubility, don't you think it moves up the plate more?
Hmm.
Pressure. The pressure has something to do with how far it moves up. Even you can be as careful as you want about measuring your solvent concentrations, because these solvents aren't generally, they're not generally pure. You generally want a mixture of them. And as close as you can get that mixture, it's still going to be off a tad. So you can't really do a table like this. So what you have to do, what is better, is to take your known samples, the things you have an idea before you do chromatography, you have an idea of what your unknown is. So what you do is you take a known sample of your material and spot it right alongside your unknown. And when you do that, if they go up the same time at the same rate, and if they stain the same way, you can be fairly sure that you can identify your unknown. Questions about that, ladies and gentlemen? Any questions about it? You guys are better than the class yesterday. I spent about an hour with them. I'm only a half an hour with you guys.
We're just absorbing it. That's all.
Okay, now let's get into the material itself. You're going to need the student data. And obviously, that's in the student data for lab section. So you're going to go all the way down. Guys, do you know we only have 2 more labs after this?
That was quick.
Yeah, it was. And I'm actually going to be sorry to see you guys go. You're my favorite Chem 1 lab on Thursdays. My very favorite one.
Your only one?
The only one?
That one, that's 2, but that doesn't keep you from being my favorite. All right, here's the chromatography dry lab data. You're going to need to pay attention to these. This is stupid, but you got to do it. All right. You got to pay attention to the colors before staining and the colors after staining. All right. So what I would do is, if you can, I would take a copy of this page, print it out, and have it there right while you're doing the quiz. Now, you're also going to have the distance the solvent moved, which is going to be the same for all of your known samples, and the distance your unknown moved. Now, what's going to happen in this, normally, if you're doing the lab, I would hand you an unknown, and the unknown would have 2 or 3 of these known samples in it, but it's in the same solution. So one solution may have copper, iron, and cobalt. All right. So what you would do on the TLC is you would spot each one of these knowns. Then you would do one more spot for your unknown. All right. So you're going to determine the RFs of each one of these samples. Note, silver does not move that much. Okay. You're going to note how far each of these moves, and you're going to determine the RFs. Then your one unknown. In this particular case, it had 3 values. There were 3 spots. So you are going to calculate the RFs for each one of those unknowns. Then you're going to compare the RFs and how your unknown stains. You're going to compare those 2 things, and if you get a match, then you know you can identify that unknown. Question about the data table, guys?
Where do we get how the unknown stains?
You're going to identify.
Or is that
Faye,
an answer?
Faye,
that-
Faye, let me go into the thing itself, into the report itself. That's where I was going to go right now. Okay.
Okay.
Bottom line, when you do a chromatography, you let it develop. Sometimes some of the solutions can be seen, others can't. All right. So what you then do is you have this staining solution that you spray on your paper. And the staining solution will react with each one of the ions to turn it a different color. Are we clear on that, guys?
Hmm.
The report itself will become abundantly clear when I go and pull it up, okay? So it'll be clear, Faye, I promise. This is going to be one of the easiest labs you do this semester, if not the easiest. Okay, so you're going to do this one. You should only see one result, and it's the one that's got the parentheses online with it. The other one should be hidden to you. So don't worry, just go for the one results. You're going to click on it and you're going to access it. And start quiz. Okay. Now, Dr. Musgrave has a very, I honestly think that he is color challenged because some of the things that he sees on this staining are different from what anybody else sees. Use that chart in the data table to match the colors up directly. You're going to be asked 2 points each, what the color of the individual ions before staining. And naturally, it's Dr. Musgrave, so they're not going to be in order. So be careful. I believe the order of the data table starts with silver, so naturally he's going to start with something other than silver. So you got the first 5 questions are the colors before staining, then the next 5 are the colors after staining. Question 11. Do you remember on the student data, there was a place for you to calculate the RFs of all 5 of your knowns? You need to put all 5 RFs in this box. Next question, you got to show how 1 was calculated. Now write this down. Remember I said silver doesn't move off the origin? Do not use silver. Use one of the other 4 to determine, to show how your RF is calculated. Is that clear, guys? The reason is silver doesn't move off the origin. So if you're going to show me how the RF is calculated, it would be 0 divided by the solvent front. And your answer is 0. That's why I want you to use something other than silver. Now, Faye, your question. All right. You're given this plate. Okay, Faye?
Yep, I'm here.
All right. You're given this plate, and this is the plate after it's been stained. So you have all 5 of your known materials. And you have your unknown. So based on the colors that appear and based upon the RFs, how far each one of these go, you have to identify all the cations that your unknown has. And guys, these plates change. So this isn't the only option. If I go in there and pull up a quiz again, I will have a different plate. And that's it. That's all you got to do. Colors, 5 simple divisions, show how one of the divisions, and identify the unknown. I'm figuring this is going to take you about a half an hour to do. Now the post lab for TLC. Sorry, I need to go in here. If I do it from there, it'll be confusing. Preview. And start quiz. Okay. First question, 10 points. Determine what the RF is of spot 3. So basically, you're starting at 0, measure the middle of the spot. That is going to be your distance your spot moves. Measure from here to the solvent front. That is going to be the denominator of your fraction, of your RF. Come up with an answer. It's going to be one of those 7. Then you're going to be doing it again. Only this time, instead of 3, you're going to do 4. All right. Okay. Question. The solvent moves 3 centimeters in 10 minutes. Why shouldn't you stop it at that time? Anybody have an answer for me?
More time allows for better separation.
Because instead the solvent, each time, each little bit of time that you're separating these things, the more time you have, the more chance you're going to get a separation of the components from one another. Now, the problem is if you take too much time, the solvent disperses the spot. So it's a trade-off there. Dimensional analysis question. Okay, basically, you've got to, it's a dimensional analysis problem. You got 6 grams per liter, change that into micrograms in the 10 microliters. So you are going to multiply 6 grams by 10 times 1e to the minus 6 liters. And that will give you your grams of solution. Then you have to change it into micrograms. Questions, guys? I'm done. 40 minutes in and we're done here, guys. Any questions about anything? Finals coming up in 3 weeks. We have heat of vaporization next week. And we have Vesper the week after that. The Vesper lab will be at a dry lab. I'm going to be talking about Lewis dot structures and valence shell electron pair repulsion. Have you guys had that yet, or is that in your future?
Yeah, we've done it in my class.
How are we doing? Everybody else? Pretty much
I
have
have
done it?
right now.
Well, we will get through, and I will, if nothing else, it'll be a good review for your test, your final test, which is probably coming up. That's it, guys. As usual, it's been a pleasure.
Thanks, Professor.
Take
Thank
care.
you.
Have a
Have a
great
good day.
day.
You have a good day too.
Have a good one.
Bye.
Thank you, Professor.
Take care, Trent. Saki, you still there? Or did you bugger off, Saki? You put me on the screen and you managed to go away. Okay, Saki, I'm stopping share. And now I am ending the meeting.